Sounds a little painful.
It was really sad, especially when you don't get it, and then it's like, oh, my calculations must be.
Oh.
Do you have 1 more minute for class?
Sure. Okay.
Actually, no.
No. Okay. So at this point, do I have to do that for the contradiction, or is that right there sufficient?
You have the entire thing has to be false, so you have to figure out how to make the entire thing false.
Oh,
The way it is right now, you cannot make it entirely false, so you might have missed one step or something.
Okay.
All right. Okay, the recorder is starting, and I got the mic going. So we'll go ahead and get started with assembly language programming. I have graded the first 2 of the 4 questions. The second one, basically fried my brain in the afternoon, so I took a little nap shortly after grading the second question. The first one was not too big of a deal. The second one was, especially the partially correct answers. The completely wrong answers, not a problem. Okay, no answers, not a problem. The ones that are partially right, like this part seems to be okay, this part is wrong, that part is wrong again, but this part is right, assuming that's what people ended up with in the previous step. Those are the hardest ones, because I have to find reasons to give points. The completely correct ones are like easy. Oh, perfect, done. Okay, so I'm still grading. In case you're curious, it is in progress. But it does take time. But the correct answers are already disclosed. Okay, so you guys know what the correct answer is supposed to be. You just don't know how many points you're getting if you are not getting the perfect answer. All right, so what we'll do today is kind of go back to the homework assignment that is due on the Tuesday after spring break. Because last time I forgot to turn on the recorder, and I felt maybe I should do this again just so that you guys know the steps to do it, so you have the commands to do it. All right, so I'm going to do this really kind of quickly at the beginning, and then we'll talk about the content of the class. So once again, I'm going to copy and paste this code. I can do this in Linux. You can also do it inside PuTTY, P-U-T-T-Y, the terminal emulator. That will work as well. So you just use a particular terminal. First thing is to make a folder, str count, string count. Oh, it's down. There we go. And the way I do it is I use the cat command. The cat command, can someone kind of guess what cat means in this context?
Concatenate.
Concatenate, exactly. So the cat command is intended to combine a few files into one longer file. You'll concatenate. Okay. So what I'm doing here is I'm concatenating quote unquote standard input into a particular file. In other words, whatever I'm typing on the console is going to be captured in that file, because the stir count or string count.s is the output file. It is redirected as the output file. So, but since I have everything in the browser copied into the clipboard, I can now paste it from the clipboard, and then it won't stop. Okay, you have to, on an empty line, you have to type Control-D to stop it, because Control-D means end of file when you're trying to type in something through standard input. So now I have the actual file. I go to stir count.s, and now we have everything here. So the key is to test your program. The first thing you want to do is to be able to load something into string, which is this label here, and Kchart, so you can begin testing your program. Your program has to precede check here, because by that time, I am going to use my script to check the content of the registers to see if you got the right answer. All right. So what we'll do is we are going to just link this program the way it is. But before we do that, we're going to create 2 test files. One test file just to specify the content of the string, and then the second test file to specify which character we're looking for. Now you can combine those into one single file if you want to. In other words, you can have one file that has exactly 257 characters, where the first 256 specify the string, and then the last character specifies the character that you're looking for within the string. You can do it that way, it does require quite a bit of crafting, if you go for that approach. So I would usually just go the opposite route, which is to create a file, one file for the string and one file for the character itself. The character, there are several ways to do it. You don't have to do it using a file approach. So I'll show you both approaches here. So I will test, I'm going to use test.0 as the input to specify the string itself. So this one is going to be, this is a rather long test string, like that, okay? So when I save this as a file, it will have the ASCII code of all the letters, all the spaces, all the punctuation, and the end of line of the first line, okay, which is a single line feed character, which is perfect because I can just change that line feed character into a null character, then I have a null terminated string. So I'm going to save this in VI. You can do this in other types of editors, okay? So I just saved it. And we need a command called hexedit to do it, because I'm using a version of my, not virtual machine, but this is actually using a Linux distribution that does not save the content, so I have to reinstall it every single time. It doesn't take a long time, it's just a quick process to reinstall it. So hexedit as a program is hexadecimal edit. It allows you to change the content of any file on a byte by byte basis or nibble by nibble basis, okay? Which can come in pretty handy. So I just say hexedit and then test.0, which is the text file, and I just go all the way to the end. You just use your cursor keys to go all the way to the end here and change the 0A, which is the line feed character, to 00. Just overtype it, okay? When your cursor is over a particular byte, whatever you type becomes the actual content of that byte. It does not save automatically. If you want to save, you type Control-X to exit and save at the same time. It will ask you, do you want to save? Click yes, and now the file is saved. Now, how do I know the hexedit was actually successful? Because the worst thing you can do is to do something like this, thinking it was successful, changing the line feed character into a null character, and then assuming that is the case, test your program. Because if the line feed character was not actually converted into a null character, and your logic is correctly looking for the null character, then you can do something that's wrong. So you might need to verify to make sure that your edit is correct. That is the job of hexdump instead of hexedit. You can use hexedit again if you want to, but hexdump can do this. So hexdump is really just a dump command. It is kind of like the light version of hexedit, where it only displays the content of a file, and you can see how the last character in this case is 00, which is the null terminator. Are we doing okay so far with these commands? Okay. All right. So now that we know everything is working, I just made one mistake. I ran all of these commands as root. So I have to check the ownership of the files again to make sure they're not owned by root. Okay, they're still owned by user. That's good, because otherwise I will have to fix those. All right. So what I'll do next is to test the program. So I would assemble steps-o string count.o string count.s, and I forgot the, oh, that's right, I forgot the colon, remember?
Oh, yeah.
I never went back to fix it. String count.s underscore start needs a colon here, so you will need to do that too. ld-o string count.o, and then we can gdb it. So when we gdb, we can put a breakpoint basically anywhere within the program, because the intent is not to run the program at all. I just want to look at how do we load the file into memory, and how do we change that one single byte Kchart so that we can specify which character we're looking for. So in this case, restore is the command that we want to use to load the content of a file to a particular memory location. So we restore, and then you specify the file name, which is test.0. You have to specify binary, and then you specify the location where we are restoring it to. It is actually it's ampersand string to specify the address where the label is defined. So, okay, I have to run it first. There we go. So now we restore that content. How do we know it's already there? Well, the X command or the examine command can double check. Okay, so we'll use that command to double check. So we have x/256, and because we know these are supposed to be ASCII code, you may not want to use BX and use BC instead to show the character rather than the hexadecimal representation of the bytes. And we want to show at the location where the string label is defined, and you see a whole bunch of gibberish because there's a whole bunch of no bytes at the end, but you can still see the beginning is THIS space IS and so on. So we have the file loaded. The most important part is the no terminator included in this content? And the answer is yes. Okay, this is the no terminator that we have specified in the file. What about the other no terminators? Well, those are by default in memory. Okay, so they have been there since the beginning. Can your program rely on those things to be there to begin with? Nope. Okay, don't rely on those things because there's no guarantee what is the actual content of this memory when your program runs. So when you specify your test string, always make sure you specify the no terminator at the end. Okay, so this part is done, and the next thing we want to do is to specify Kchart. So we want to take a look at what is at Kchart right now. I think most people have a pretty good idea of it is just 0 at this point, but we'll double check. So Kchart is 0 for sure, okay? So you want to change it to something else. If you want to look for the character, let's say lowercase a, then you want to change it to lowercase a. There's a certain thing called set var to change the value of a variable. But remember, in GDB or in assembly language programming, there's no such thing as a variable anymore. So you can't really do that. But what you can do is to dereference labels. Okay, so you basically say I want to store something at the address of, and now we go back and specify what address are we talking about? String. Okay, but you have to remember to use the ampersand, because if you do not use the ampersand, the assembler will give you a 0 and it doesn't know what to do with it. Okay, but this also has a problem because without type information, the assembler doesn't know what type of pointer or what type of address we are dereferencing. And the default is an int, which is 33Y. We don't want to overwrite 4 bytes. We want to overwrite exactly just 1 byte. So the way to do that is to cast the address into a character pointer first. So when you dereference it, it becomes a byte. Now we can specify that we want to specify lowercase a in that location. Press the enter key, and then we double check using the previous command. Oops, that did not change. That is, oh, I used the wrong variable, Kchart. So I accidentally changed the string, and yep, there we go. Did you guys see my mistake? Okay. But the idea is the same, okay? You use the command set var and then use the typecast, the dereference, and then the label in order to specify, oh, I want to change that one single location to the following content. Is that okay? So once you get used to these commands, okay, you can either type it every single time when you test a program, which is very tedious, or you can put it into a script where you can just recall it, whenever you need it. I think last time I kind of demonstrated how to do it. I'll do it again today because I think it's a great tool for you guys to speed up your development cycle. Even within GDB, you can shell out. Okay, in other words, you can open a new shell to do certain things and then come back to GDB when you're done with that shell. In Linux term or in Unix term, it's called shelling out of a particular program. And in most environments, it is using the exclamation point to shell out. So I'm going to shell out and run vim because that's my editor. Yep.
Can you shell out into another instance of GDB?
Yes, you can. In fact, you can shell out to GDB exactly the same executable because those two processes are independent. So you can do it, but it's kind of confusing because you cannot tell which GDB session you're in when you're in there. Yep. So you can run any command you want. So in this case, I just want to edit a file, and I'll call that debug1.gdb. The extension GDB is not necessary. I just use GDB so I can tell this is a script for GDB. Okay. And this is just a text file. Type whatever you normally do on the keyboard, okay, inside GDB, and it will run it automatically when you say source and then the file name of this script. So in this case, I just want to reload the content into memory, which is restore, and then the file name test.0, specify binary, and then specify the location where it's supposed to go into. And then the second one is to set up a particular character to search for, and that's setvar dereference typecast the address of Kchart equals to lowercase a. Okay, I just choose lowercase a in this case. Now, obviously, you can set up multiple of these source files. Once you set up one, just copy it, okay, and then make variations of it. So this way, you can test your program in multiple different ways without having to retype everything by hand every single time. All right, so this is all done. Exit the editor. Now I can make use of it. I can say source debug1.gdb, press the enter key, and it would have done everything that it specified in the file. So it's a very handy way to repeat certain commands that you run a lot of times, and it's kind of long to type. This is a great way to save your time. Are there any questions about this? Now, if you really want to automate even more when you're dealing with testing a program, you can go back and change the program even more, the script itself even more. So what you can also do is to say specify run. By the time it gets to a particular breakpoint, the first breakpoint, hopefully it is checked here, you can say print $ECX. Okay, when you want to print the value of a register, using the print command, you have to precede the register name with a $sign. Or you can use IR, okay, I space R space ECX, which will do the same thing. This gives you a little bit more option because you can, if you know the correct answer to begin with, you can actually do something like this. If you know the correct answer is supposed to be 5, then you can say, yay, or oops. So your test script can now give you actual feedback. Is it working or not? Okay, but you don't have to go that fancy, right? I mean, if you just want the basic version, you know, real basic, then you just have to say IRECX, and then you have to look at the value and see whether ECX has the correct value or not. Are there any questions? Say again? Stop?
Step, like S.
Single step?
Yeah.
Yes, you can, but it's unconditional. So when you specify S here, it was just single step, but it is not interactive. So it may not be very helpful. Single stepping may not be helpful inside a debug script. But the first part is definitely helpful. You know, reloading the content from the file into the string, that can certainly be helpful. Okay. Are there any questions about setting up your homework assignment, how to test it, how to load the test string into memory, how to specify the character that you're searching for, and stuff like that? Yep.
The way it looks on Moodle right now, it looks like we have 3 weeks to do that. Is that a mistake?
I think so. I miscalculated the amount of time.
Because it's not the week after spring break, it's the week after the week after.
Oh, that would not be right.
I mean,
Okay.
we'll take that, but
Well, that means, you know, you probably will end up with simultaneous homework assignment after that.
yeah.
It's not good in the long run, so I'm gonna change it back to just the.
No, that's further in the future. You don't want to do that.
On the 29th.
Yeah.
Yep, on the 29th, I'm actually meeting with the Liberal Arts Replacement Building Design Committee the second time to decide on.
Could you
other
make it
things.
on that Thursday instead? 'Cause on the 29th, 4:40 has an
Yeah.
assignment due.
That would be cool.
So just so it's a day off.
Oh, okay.
2 days
I
off,
see.
yeah.
Because of 440.
Yes.
Yeah.
Okay.
Thank you.
I don't think this one is going to take too much time. Did I show you the C code last time? You know how to write the C code first?
No.
No? Okay, so we can do that. All right, so before you do this in assembly, the first thing you want to do is to do it in C. And because cisp310 is a prerequisite of this class, I'm assuming that all of you now know how to write program in C or C++. And this is not a very difficult algorithm, so I'm assuming that you know how to write that code. So I would do it for you this time, but in the future, there will be occasions where I just specify what it is supposed to do, and then you have to come up with a C code, and then convert it into assembly code. Okay? But for this one, I can just give you the C code, just so that you can get a head start on this one. Okay, so I'm going to use a C code here. Here's the function. It returns an integer, string count. It requires only one single parameter, which is a string. Oh, 2, because I need to know which character I'm looking for too. So const char, Kchart. Okay. And I'm going to use even the same names as in the assembly code. So this way you know which one is which one. Okay, so how do we get this done? I guess if I show you the recursive version, it won't be very helpful because we are not doing recursion in assembly, not yet. We will, we will at some point, but not yet. So I'm going to use the iterative version of this because you have a particular register to keep track of the count. So I'm going to do that. All right, so we'll use a integer called ECX as my counter. Okay, I think that's pretty obvious. Yes? No? Kind of?
Yes.
Okay.
Do we have
And
to
I'm going to have a pointer.
Do we have to initialize that to 0?
Oh, I'll do it later. It is not my style to initialize it when I declare. I usually have a separate initialization. That's just personal preference. Okay, so we have a register EAX that's already initialized by the time it gets to your code, so you don't have to do this in your own code. All right, and we want Kchart to be in a particular register. I think it's BL. So BL is that register. So this part is already done. EAX is string is already done before your code gets control. BL equals Kchart is also done already. The other thing I can also do is just to change this to EAX. I'm not going to do that. All right. We also have to initialize ECX to 0 because that's my counter. And the way to do this, I can do it in a single loop while star EAX if star EAX equals to about, yeah, I'll do it the easy way. I don't want to make this too difficult to decipher. Plus ECX. ECX. There we go. And to be consistent with what I preach in my other classes, I always use curly braces, even when there's no need to use curly braces, just to clearly indicate the beginning and the end of a construct. So I'll just make it consistent with my recommendation. Is that okay? Does it look right to you? So the loop is saying, as long as EAX is not pointing to a null character, do the following. The following is, if EAX is pointing to a byte that is the same as the byte specified in BL, increment the counter. But I'm forgetting one thing. This is an infinite loop. Assuming the string is not a null string, it is an infinite loop. What am I forgetting?
You're forgetting to increment EAX.
Exactly, because otherwise EAX is not advancing. So we have to increment EAX over here. There we go. Okay, good job. Well, just because I claim this is the right logic doesn't mean it is the right logic. So I will go ahead and test it. Well, to a certain extent, this is not a proof that the algorithm is 100% correct, but it is nonetheless, just a test to see if it's right or not. So I'm going to say x equals to string count, and I'll specify this is a rather long string, exactly the same one as I used in my test case in assembly. And the character I'm looking for is just lowercase a, which is also what I used earlier to specify Kchart. So we can do a manual count right now just to make sure that we know what the expected answer is supposed to be. So here's 1, 2, so there are 2 lowercase a's in the string. So we'll go ahead and test this program. But how do we test this program? It has no print in it. GDB, exactly, okay? Using printf or cout to test programs is not a good idea, okay? As far as I'm concerned, it is not a good idea because you might be told by other professors that it is okay. There's some kind of buzzing sound. Oh, it's me. And I can tell you what is making that buzzing sound. It's my little Vader keychain thing. That's it. Yeah. Yeah, so it was me, sorry. And I thought I was just hearing things in my mind. Okay, so we're going to test this program to see whether it works or not in GDB. So GCC, this is just a regular C program, it's not even C++. Dash G will do the same thing as G steps. It will help retain the symbol table for debug purposes. I can specify dash O to specify the executable right away. And the source file is string_count.c. Okay. And now we can go into GDB, string count, and this time it is the executable from the compiling the C program and not from assembling the assembly version. List the program, obviously this is in C, put a breakpoint on line 27, run the program, no seg fault, good, that's good. Print x, it is in fact 2. So the program does work, okay? Are there any questions about the C version of this program? Okay, so your job is to convert the C code into assembly code. So you have to look at the control structure. Let me get out of GDB and go back into the source code. So you have to look at the control structure of string count. Don't worry about the parameters, okay? We are not at the point yet to talk about parameters. So all that stuff is already initialized into the registers. So what you need to do is to say, okay, knowing the registers have certain responsibilities, how do I write this code? And it should be fairly easy, I would say, in this case, because you don't need to you don't need to access memory other than dereferencing a register. So that makes things a little bit easy. Yep.
Isn't it possible to see how the C compiler did that implicitly?
It won't help because in this case, the C compiler will make use of variables on the stack. And if someone turns in that code, it will stand out like a sore thumb that has been burned and split open. I can tell. Oh, that used to be a thumb. So I'm not too worried about that. Any other questions? No one is. Yeah, go ahead.
I know like in C++, when doing the comparisons, it doesn't really matter which side, like what's on which side. Does that matter in assembly?
Sometimes. Sometimes, because there's one type of value that cannot be the second operand? Can you guys guess which one cannot be the second operand? With all the operations that we have done so far, move, compare, subtract, and add, the second parameter is always the destination. Even in compare, it is the quote-unquote destination, even though it is not storing anything. So what cannot be stored?
No, I had a different question. Sorry, I don't.
Oh, okay. A constant cannot be stored, but how do we specify a quote-unquote constant or an immediate mode operand in assembly? The $sign. So whatever starts with a $sign cannot be a second operand. It can only be the first operand. Everything else can be either first or second. There's also one more restriction that doesn't really come into play here. You can only have up to one memory operand. It can be a direct operand where you specify, hey, this is the address where you're supposed to go, or it can be an indirect operand where you say, hey, this is the register. Use it as a pointer, go to that place to get something. But in either case, it is a memory operand. In any instruction, you can have up to one memory operand, which means if you're trying to copy where one register points to where someone else points to, then you have to separate it into two operations. It doesn't happen here. You should not run into that problem in this code. Yep.
My question was, you gave us some code on Moodle. How much can we change that?
You mean this code here?
No, the Moodle code, the
Oh, the
assembly
Moodle code. Oh. You can change just about anything, except by the time we get to check here,
Okay.
ECX should have the number of characters in the null terminated string.
Okay, so
The
we're pretty
number
much playing in between like the move byte and check here, and we can add whatever we need to.
Everything from start, you mean?
Yeah.
Yeah, so everything from start, which is missing a
Yeah.
a colon, all the way to check here.
Okay.
Because my script is going to stop at check here. Well, yeah, so my code will stop at two places. When I grade your homework assignment, the first breakpoint is at _start, where I will use restore to set up my own test case and set up your Kchart. So you don't want to change the name of the variables at all because my script will rely on those labels. And then I will do a C to continue running until it hits the second breakpoint, which is going to be at check here. Now, because I set up the test cases, I know the number of characters expected, so I can check your ECX value against what is the correct answer, and that's how I'm going to test your program. And I'll give you multiple test cases, and each one has equal value within the homework assignment. So it's going to be evenly distributed across the test cases. Is that okay?
Yes.
Okay, all right. Any other questions? No other questions? Does anyone want to see the recursive version of string count? No? Yes? Okay. It is actually easier, simpler, and in many ways makes more sense than this version. So I will do the other version kind of side by side. Let's do it side by side. So we'll do a vertical split of the screen. Go to this part here and do it in, whoops, I don't want to delete it. I want to make a parallel version of this, and I'll call that recursive string count. Same parameters. Okay, we have a string, and we have a character that we are searching for inside the string. And I'll do it with one single return statement. Okay, well, I mean, it can be done with one single return statement. So here's a return statement. So with a recursion, you always ask the question, when do I stop? Okay, what is the simplest case where I have the answer right away and I can say, yep, this is the answer. So in this case, when can I stop? What is the special case where I can say, okay, I know the answer to this one. I don't need to call myself again.
When you reach null.
When it's null, exactly. When the string itself is an empty string, which means string is already pointing at 0. Okay, so let's do that. So that's confirming that string is pointing to 0. I know you're not used to this, but if you think about it in C and C++, what is What is exclamation point? It's logical not, right? Logical not will turn anything non-zero into zero, anything that's zero into non-zero. Okay? What is asterisk string? It's dereferencing a pointer to a character. Okay? So this means the entire thing is true if string points to a null character, which is what I want, because I want to confirm, hey, are we at the end of a string? Is this an empty string? Well, if it is an empty string, what is the answer? How many characters we are looking, can I go back? What is the number of characters, Kchart, that we should be returning? Now, here's a gray area, okay? Because I did not specify in the homework assignment, but I will specify here. Kchart cannot be null. Okay? If I tell you already that Kchart cannot be null, what should I put here after the question mark? This is a ternary operator, which means I'm specifying the value to return as the entire expression when the first part to the left-hand side of the question mark is true. What should I be returning?
0.
Good. Make 0. Okay, very good. So we'll put a 0 here. So that means the other one has to be the recursive part. Yep.
Then you have to add the call itself, add and then call itself.
Okay, so you have to call yourself for sure. Okay, so we'll go ahead and call ourselves first. So we call ourselves, but when you call yourself, you better change something in the parameters, because otherwise it becomes infinite. So the only thing we can change is really the first parameter, because we cannot change what we are looking for, but we can change the starting point of the next invocation to be 1 byte after the current one. So we'll keep Kchart. Okay, so that part is right. But this is not the entire answer either, because this will only count the number of Kchart in the rest of the string. What about the one that string is pointing to right now? I don't know whether it matches or not, so I need to check. Okay, so I'm going to say add, use another ternary operator, but I'll use parentheses around this one so it's clear that this is a nested ternary expression. So then I say, hey, I know I'm pointing to something. Is that something Kchart? If so, give me a 1. If not, give me a 0.
Is the second ternary operator part of the second result?
Yes.
Part of false?
Yes.
Okay.
So in other words, there's a implicit parentheses or an implicit pair of parentheses here. Oops, there we go. That's it. See, look at the assembly. Look at the non-recursive side on the left-hand side. Look at the recursive version on the right-hand side. See how clean it is, short, and easy to understand.
Technically one line.
Technically one statement. How many statements do we have on the other side? Even not counting EAX, EBX, and combining the initialization of ECX in the declaration. It still has the while as a statement, the if as a statement, plus ECX is a statement, plus EAX is a statement, and the return is a statement. 5 statements. And then the other one only has 1 statement, which is just the return statement. Yes, it has nested ternary operators, but it is still 1 statement.
So it's harder to debug.
Oh yeah, it's harder to debug. You cannot set up breakpoints. The debugger in C does not let you set up breakpoints within an expression. So yeah, the second one is a little harder to debug. You can't stop. You can only stop at the return statement before it does anything. So technically you can still debug it. Yep, it's just more difficult. Yep. All right. So are there any questions about the recursive version of string count? Yep.
What we know now, we won't be able to implement it
At this point, we are not capable of turning this into assembly because we have not talked about subroutines yet. All right. Any questions about string count? I don't think it would take you guys too long to do it, but if you try to do it today or get it done, then you don't have to worry about it in spring break. Okay, which may be enough incentive for some of you to get it done today. The rest probably will try on Monday after spring break. when you try to recover from the spring break. Alrighty, so this is all done. And we are ready to move on in terms of class material. So we are pretty much done with assembly language programming, the basic stuff at least, because we have talked about control structures, we talked about how to, the multiply and divide, I'm not too concerned about it, so we're not going to worry about it. And so today we'll move on to subroutines, okay? But we are not using subroutines in string count, okay? Just keep that in mind. When we talk about subroutines, there are lots of interesting topics. The first part only talks about subroutine call and return mechanism, the concept of a stack, stack pointer, push pop, return address, and so on. So we'll start with a discussion of the stack itself. How many people were introduced to the concept of stack even in cisp310? No one talked about the stack in cisp310?
Even you did.
Some people.
Even you didn't.
I did. I talked about frames.
I think though, you went as far as just multiple files. That's about it, but not really stacks. Or allocating memory at all.
Did I talk about recursion?
Well, yeah, you did talk about recursion.
Oh, I cannot talk about recursion without talking about a stack. All right, so we'll basically start with the beginning, to talk about what is the stack. The stack, if you look at this slide, I have not opened up the links yet. These are not fixed at this point. So let me see. Let me unlock it first, okay, because I keep forgetting to change all of these. All my notes will change again in the next 2 years because the district is changing from D2L to Canvas.
Oh.
Yep.
I've heard of Canvas. It sounds a lot nicer than D2L.
But not compared to Moodle.
No, Moodle's beautiful.
Well, I don't really care much about whether it's, whether it looks good or not, but
Yeah.
functionally speaking, Moodle is not bad. Has a lot of features. Okay, so I'm gonna I'll fix it one at a time, okay, the stack. So this is the note on stack. And you can basically access, the rest of the notes here. So instead of just reading the notes, I'm just going to explain the concept first. What is a stack as opposed to what is a queue or FIFO. A stack is also known as LIFO, which is last in, first out. A queue, on the other hand, is known as FIFO, which is first in, first out. So what is the difference? Because a lot of times we look at these terms, it's like, okay, last in, but what do you mean by last in, first out? What do you mean by first out? The best way to look at a stack is a U-Haul truck, okay? If you have moved or have helped somebody move, you will know that, if you load up a U-Haul truck and you say, okay, here's the map to the destination. I don't want to lose that. It is important. So I'm going to put it here in the truck because this way I won't lose it. I won't forget to bring the map with me. Okay, so you put it down into the, they call it the granny's nuke or someplace like that, in the U-Haul truck. Yeah. Sorry?
Mom's attic.
Mom's attic. Okay, very good. Okay, so you put it there. You just make sure that, okay, this way I won't forget to bring it. And then you load up the truck. Okay, and then you push the bicycle, which is usually the last item, and then you slam the tailgate, shut, and you go like, okay, we're ready to roll. And then you get into the driver's seat, and you go like, where are we going? Oh, that's right, we need a map. But then remember, I put the map into the truck already. Right, it is in the truck. Where is it? It's in Mom's attic. It's the first thing that you put onto the truck. So how do you get back to that map?
You don't.
You have to unload the entire truck. That is last in, first out. Another prime example of last in, first out being a very annoying thing is a refrigerator. Unless you're very disciplined and finish the food item, wait until the fridge is empty, and then you buy new stuff and put it in. Most people don't do that. Okay? So what do we do usually? Okay, you finish something like milk or bread or something. Okay? So you go buy milk or bread or whatever. Do you have a designated place to put your milk? Okay, some people do, some people don't. Okay? So we usually end up with the most recently bought items at the front part or the easily accessible part of the refrigerator. What do we have in the back of the refrigerator? The rarely used items, or the item that you used 2 or 3 years ago. So they typically look like a mowed garden of varying colors. Right? That's also last in, first out. Okay? So last in, first out is inconvenient in many cases in real life, but in computer programming, it is a very useful data structure. Okay? A lot of times we rely on last in, first out. Functions in C and C++ is last in, first out. What in and what out? Okay, how about we change the in as call and we change the out as return? Last call, first return. Isn't that what we know about functions? Okay, the return is going to return to the immediate place where it is called. Okay, so that's why last in, first out, or the stack has so much to do about, that's why it is related to function call and returning. Okay, so we'll talk about the next few topics. The next one is called the stack pointer. There's one designated pointer or designated register called ESP. It is the stack pointer. E stands for enhanced and SP stands for stack pointer. It contains the address of the last byte that you store on the stack. Okay, that's what it is. Okay, it always points to the very last byte that you store on the stack. You can also interpret the value of ESP or the stack pointer as the address of the next byte to remove. The stack grows from top to bottom. In other words, it's when the stack is empty, the stack pointer has a high address. When the stack starts to fill up, the address will go lower and lower and lower. So the most recently pushed item is going to have the lowest address on the stack. Okay, there's one particular reason why it's arranged like this. It is not counterintuitive. The ESP is also known as a general purpose register, which means all the instructions that we have talked about up to this point, the move instruction, the subtract instruction, the add instruction, and even the compare instruction can all be applied to the stack pointer. Is that okay? Okay, all right. So now we move on to the next slide. These are specific operations that you can do with a stack. Pushing a value onto the stack is to store a value on the stack. To pop a value from the stack is to retrieve a value from the stack. So push is the same thing as quote-unquote store, and then pop is the same thing as retrieve. But you have to use the last in, first out order. So pushing is always pushing the last item onto the stack, and popping is always popping the most recently pushed item from the stack. Is that part okay? Just terminology. Push is to store, pop is to retrieve, but we still have to remember to follow the last in, first out order. The last paragraph can come in handy sometimes because we only have a certain number of registers, and sometimes you quote-unquote will run out of registers. When you run out of registers, you can also use the push and pop instructions to temporarily save the content of a register on the stack, make use of it in some way, and then pop its old value back to restore the value. So this is a place where you can just say, hey, I need this register for this thing here, so I need to remember where, the previous value, push it on the stack, use the register, overwrite the value, and then later on retrieve the old value of the register from the stack to restore the value. So it's a very handy trick that people use in assembly language programming. So in these subsections, push is actually an instruction. Push expects one operand. It can be just about any operand because we are dealing with a cisp architecture here. So that means I can push a register, I can push a constant, I can push an indirect operand, which means the actual value pushed is the content pointed to by a register. I can also use a direct operand. So push can use any one of those particular operands. Push F, I'm not going to talk about it too much because it pushes the status flag register. In this class, we are not using push F much, so we'll just kind of skip this one. Push A also has no operand. It pushes all the registers onto the stack. What is the use of push A? What do you think is going to be, why is it useful? Under what circumstances, do we need to push all the registers on the stack?
A new function call where it's recursive.
Well, in most cases we don't do that. We have designated certain registers to be the responsibility of the caller to preserve, and other ones we designate to be the callee's responsibility to preserve. So we typically don't want to push every single register because that's a lot of overhead. Yep.
Oh, I was just gonna say maybe it adds a null in there so we can distinguish between two different calls.
Not exactly. Yep.
To reuse the references?
To what?
Reuse.
To reuse the registers. Very good. Okay, so this is leading to something else. Okay, so under what circumstances do we need to reuse not one, not a few, but all of the registers? It has to do with a modern computer, operating system architecture. Multi-threading. Okay, multiprocessing is kind of one of those things, but multi-threading is the actual concept that requires the use of push A. So what is a thread? Has anyone worked with multi-threading in this class? No? Okay, that's okay. Okay, but basically one thread is like one path of execution in your program. Now most programs, including all programs that we are writing in this class, and probably all programs that you are going to write on this campus are single-threaded, which means at any point of time, there's only one point or one line of execution in your entire program. Is that making any sense? So when you stop in GDB, that's the only place that the program is executing. But in real world, a lot of programs are multi-threading, which means the same program has multiple lines, has multiple threads that are executing at exactly, quote unquote, exactly the same time. But there's only one processor. How can you be executing multiple points of a program when you only have one single processor? Assuming there's only one core, because there are single core processors even today. So assuming you only have one single core, how do you implement multi-threading? Time sharing of resources. And one of the hardware resources that has to be time shared are the registers. So when you switch from one thread to another thread, you need to say, hey, I need to save the state of all the registers of this thread that is losing control. And then once you are done with that, you have to restore all the registers from somewhere in memory of the thread that you are resuming. So the instructions that can be useful in this case is the push A instruction, because this will push all the registers into memory. Then you use a pop A to do the opposite in the restoring thread, so that you can just use single instructions to do what we call a context switch. Okay. So I'm not going to test you guys on multi-threading. I just want to give you a context of why we have instructions like these. Pop is kind of the opposite. So pop expects one operand that either specifies a register or a memory location. It cannot be immediate because we cannot pop or change constants. So that's why a $ type of operand cannot be in a pop instruction. It pops a value from the stack into the specified register or memory location. Then we have a second instruction called popf. It pops the status flag. Once again, we're not going to use it much in this class, so we're not going to talk about popf. Pop A is the opposite of push A. So instead of saving all the registers into memory, this one is reloading the states of all the registers from memory. Once again, it is useful for context switching in a multi-threading type of program, but in our cases, it's not really that particularly useful. Okay, so now that we have talked about the push and the pop instructions, and we have talked about the overall stack operation, let's go ahead and run a particular test program, just so that we can see what is changing when we push, what is changing when we pop, and what is going on with the stack itself. Okay, so this is all kind of hands-on. All right, so we'll go ahead and I'm just going to make a new folder here called test stack. Oops, test stack. Okay, here's the first one. The first test program has .global start, and I'm not going to do much here. It's just push L. Remember, with push instruction, I can specify constant. So I'm pushing a particular constant here onto the stack. I'll give it this very specific hexadecimal pattern. Okay, so this is a 32-bit constant that I'm pushing onto the stack. And then we'll pop it. But when we pop, we cannot pop it into a constant, because wherever it pops into has to be something that can store a value. So it can be either a register or a memory location. Since I really have not allocated any type of memory location, let's just pop it into a register. Let's say EX, okay? All right, so that's the entire program. The exit code of a normal program really should be this, which some of you have seen and asked and say, okay, but what is that? That is equivalent to exit 0 in a C or C++ program. Okay. So this is my entire program. Obviously, the focus is going to be on the first 2 instructions and not so much the last 3 instructions, because we will get to those later on, but not today. So let's go ahead and see what happens when we run this program. GDB, oops, we have to assemble first.
Pleasure.
Invalid instructions suffix. That's because I'm not using a 32-bit mode, and that's why it doesn't like it. I'll just go ahead and run it in the emulator. Okay, I'm just starting up the emulator and run the same thing in the emulator. Yes, once again, my emulator runs faster than yours. Unless you're using a Mac, because you don't need an emulator. Or you have an accelerator too on the Mac. All right, so the next thing we'll do is to show you a trick to move your project quickly from one Linux environment to another Linux environment. It really kind of shows you the flexibility of Linux, or the command line in general. So we have test stack here. All right, so we'll go ahead and go to the parent folder of what you want to transplant, and we'll do everything with one single line of commands. The first line is a tar command, which most of you already know. ccvf, which is create, Z is compressed with gzip2, V is verify, which is something that we don't need to specify, F is to specify the file. But this time I specify a dash or minus as the file, which is standard out. Okay, so this means instead of creating an actual file in the file system, whatever I'm creating is going to the standard out of this particular console, which means if I don't do anything with this, it will just show some gibberish on the screen. Okay, And the folder that I am, or the folder directory that I'm archiving is test stack itself. So this is going to create an archive where the output is to the screen, quote unquote, screen itself, which is not very helpful. So I'm going to pipe it. In other words, the result of the first command is going to serve as standard in to the second command. The second command is SSH. Okay. And SSH is kind of like PuTTY. We specify the port number, 2200. We specify the username, which is user. The network address is localhost. And usually we just end here. If I want to open up a terminal and do something, I just stop here. But this time, I don't want to just open the terminal. I want to run some command, just straight out from this particular command here. So that has to be quoted using a double quote. And then I can specify the command that I want to run. It's tar again, but this time it's xzbf, which means I'm extracting the file instead of archiving the files. Once again, I don't specify an actual file, I specify a dash here. But because the operation is x, which is to extract, the dash is not specifying an output file anymore, it is specifying the input file. And if you are specifying the input file to be a dash, it is standard in. It is the standard input file, otherwise known as cin in C++, or just stdin in C itself. Okay. Or file descriptor 0, okay, if you will. I think that's it. I think this should do it. So we'll give it a try. It asks for the password on the other side. Type in the password, and it is supposed to be done by now. Okay, so we'll log in to the other side and see whether it is really done or not. So the login is just ssh-p 2200 user at localhost user. Do ls. You can see that the folder is already here. So let's check whether the files are there as well. Test.s is here. So as gstabs-o, test.o, test.s. This time it assembles without a problem. So the problem that we saw earlier was because the operating system was a 64-bit operating system, which also implies the assembler is a 64-bit assembler, where it does not recognize how to do a push long instruction. It does deal with move long, just not push long. Then we do the link, and we run gdb. Whoops, we have to specify gdb test list. Put a breakpoint on the very first instruction, or we can just specify the underscore start label. Run the program, and we are now ready to run the first command. If I just run this command, it's not going to show me anything. So instead of just running the command, I'm going to show you what is the stack pointer. Because remember, the stack pointer points to the last byte that was pushed on the stack. I haven't pushed anything yet, okay? But I still want to know what the stack pointer is pointing to at this point. So I can just do IRESP to look at the register. Okay, it looks like some kind of gibberish random value, okay? But there's a certain pattern to it we will see later. Okay. And then we single step this instruction. Single step. And you can see that nothing seems to be happening. But we want to check ESP again, because according to what we just talked about earlier, when we push items on the stack pointer should go lower and lower. Okay, is that okay? Does everybody remember that discussion? When we push items on the stack, when we store items, we are decreasing the stack pointer. Is that okay? All right. So we'll go ahead and check and say, okay, so where is the stack pointer pointing to now? The stack pointer always stores an address. It used to be pointing to the location ending with A0, and now it's pointing to a location ending with 9C. What is the difference between A0 and 9C in hexadecimal? 4, okay. And push long, the L, what does it stand for? It stands for long, and long is how many bytes? 4 bytes. So it makes sense, okay? All right. And I also said, yeah, go ahead.
So like if you did like push W or push B, then it grows. It grow down by that amount instead.
Yes, that's a good observation. But there's no push B. You cannot push a single byte. You can push a word, but not a single byte. In the 64-bit mode, it doesn't even let me push a long. Okay, and there are reasons why it does not let you push smaller items on the stack. We'll get to that. Okay, but right now we are kind of focusing on what do you think is at that location? Blah 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 79C. Remember the definition of the stack pointer. It points to the last byte that we pushed. Okay, so we pushed 4 bytes, not just one, but it does point to only the very last one. So that means those 4 bytes should be the constant that we just pushed on the stack. So I should be able to find F2, 1D, 26, D0 somewhere on the stack. In fact, not somewhere, exactly where ESP is pointing to. Can someone tell me which command in GDB I should use to examine that portion of the memory locations? The X command, right? So we want to use the X. If I want to look at those as 4 individual bytes, I specify 4, which is the count, and then I specify 4 bytes, display each byte in hexadecimal. And to specify the address, instead of repeating or just hand type 0xDFFF F79C, I can just say $ESP. Okay? Because $ESP is how you refer to the value of the stack pointer in GDB. It's very handy because you don't have to retype those long hexadecimal digits. Press the enter key and we see, oh, D0261DF2. Things are kind of mumbled up here because we're supposed to see F2, 1D, 26D0. Why? Because of little endian. Okay, because we store the least significant byte at the lowest address. And in this case, D0 is the least significant byte. That's why it has the lowest address, which is the one ended with 9C. 9D has 26, 9E has 1D, and then 9F has F2. Yep.
What was the ESP again?
ESP stands for Enhanced Stack Pointer. Basically just a stack pointer. Yep.
So basically like the stack pointer, like much like the little endian, will also be pointing to the least significant bit of.
Yes. Yep. So you will see that the little endian standard is really uniform and universal in the Intel architecture. Everything that it does is little endian. Okay. All right. So that's kind of cool. And the next instruction, which you can see on line 4, is a pop out instruction. In other words, we want to restore or retrieve the last item that we push on the stack and put it into, in this case, register EBX. So you probably already know what it's going to do, okay? Before the instruction, I kind of want to take a look at what is EBX. It is 0 at this point, single step, and without much surprise, it now has the content of F2, 1D, 26D0. Okay, that part is not surprising. What about the stack pointer? What do you think is the current value of the stack pointer now that we have retrieved that item from the stack? We will go back to the original value. Okay, but let's double check because we just want to confirm that. It's back to 7A0. Okay, next question. What about the content that was at location 9C? Is it still there or not? Okay, so that's a good answer. But a better answer is, why do we care?
Well, we don't care, but is it still there?
Well,
Maybe.
Like, well, pretty much like would we care because like if it's technically still there after we like move the stack around, it's still holding like it's still like eating up memory somewhere, or?
Well, technically, we do not care because we really should not count on any content to be retained below where ESP points to. In other words, if ESP points to a particular location, you really should not care about the content below that point. even in this case, I already know that it retains the same content as before after we pop. You should not count on that. And why? Now it's not a really fair question because we really haven't talked about the concept that will invalidate this assumption that we can retain the value of the stuff below where the stack pointer points to. But I just want to give you guys a shot, and see if anyone has an idea why that is the case.
Just like total shot in the dark, like are those memory locations, like once the stack pointers move, like are those memory locations accessible by like other parts of the program, like other registers and things?
Exactly. Okay, so basically, if it is below where the stack pointer points to, it means it is available for other things to make use of it. But what other things are we talking about? This is the only program in execution. Well, there are things that happen that your program has no control over. Okay, so I'm moving that topic just a little bit ahead of time. We will go back to that when we have to talk about it. The concept is called hardware interrupts. Okay, how many people have heard of the term hardware interrupts in the context of programming or configuring a computer or something along that line? Yes? No? Okay. Some of you might have done that, because in the older days of, well, even now, if you go to the device map in Windows, you can actually see what interrupts a particular device can generate. Okay, but it doesn't explain what it is. So what I'll do is I'm going to explain what an interrupt is and why it has any relationship with what we are talking about here. Okay. Think about DOS. Back in the good old DOS days, which looks just like a command line interface, except you have one and only one command line interface. So what do you think DOS has to do to see if you're typing anything on the keyboard? The keyboard is a hardware device, but it is readable in software in a certain way. So what do you think the software has to do to see if you are typing on the keyboard? And if you are typing on the keyboard, it has to remember what you're typing, so that when you press the enter key, it will know, okay, we have to execute that command.
It's like
so,
full-frame clip. It's like full-frame clip.
Yep, it's polling. Okay, it is doing what we call polling, P-O-L-L-I-N-G, for input or for changes of the input. Okay, in other words, it's stuck in a tight loop to ask the keyboard controller, hey, is any key pressed? If the answer is no, it goes back right away to that question. Go, is there any key pressed? No. Is there any key pressed? No. Is there any key pressed? And you'll keep doing that until you actually press a key or until you turn off the computer. Okay? What is wrong with this approach of doing things today? It was okay back in those days because DOS has only one single console. There's only one person who can use it for one particular thing at a time. Yes?
And there's not only one input.
Exactly. So we are doing stuff in the background, right? So if your command line interface is chewing up all the processing time by repeatedly asking the keyboard controller, is there any key pressed, then the rest of the computer won't have as much resources to do anything. And how would this approach impact your battery life on your laptop computer? Because I can see a few laptop computers around here. So what if your laptop computer or your phone is constantly asking the touch screen, is there any event? Is there any event? Is there any event? What is going to happen? And it's doing this at top speed, right? 2 gigahertz, using all 4 cores. What do you have instead of a phone?
Hand warmer.
A hand warmer, exactly. You have a hand warmer that is probably too hot to touch, okay? Because it's chewing up all the processing resources just to ask that simple question. What is a better approach to do this? Okay, let's not think about keyboards. Let's think about like office hours, okay?
Just like wait for somebody to poke you, hey, I got an assignment.
Exactly. Okay, so if you think about office hour, I mean my office, so do I call out to the hallway and say, is there anyone out there and do it all hour during my office hour?
Not anymore.
Not anymore. Okay, very good. Okay, I learned my lesson. Okay, I don't do that anymore. So what do you guys do instead? Because you are the event, right? You know, you're the thing that I can activate. So what happens instead? You get to my office, you knock on the door to get my attention, right? So that's a much better use of resources because I can just take a little nap in my office when nobody is asking questions. And I can just wake up and, you know, answer a few questions and then go back to my nap to conserve power so I don't become a hand warmer. Right? So the same thing, same thing applies to your keyboard, your touch screen, and stuff like that. So using a touch screen, which is an easier prop to use, or any hard button on your phone, okay? There's no polling going on, you know, in Android asking whether the power button or the volume up or down button is being pressed or not. There's no, the operating system does not ask that question. What happens when I press that, okay, is it generates what we call an interrupt. In other words, some hardware circuitry will detect a change of the button, which is pretty easy to do, okay? And what that's going to do is it is going to call a subroutine in the operating system. So instead of using call, C-A-L-L, as an instruction, the hardware itself is triggering the same mechanism of calling a subroutine. Is that okay? And that subroutine is in the operating system, is in the kernel itself, and what it will do is it will try to figure out, okay, which button is pressed. It will go figure out which button is pressed, and then it will figure out, and then it won't do a single thing, it will put that event into a queue, and the interrupt handler is done. But what happens is when the interrupt handler returns, the operating system gets a chance to say, oh, is there anything for me? And we'll find out that there's an event in the queue, and then we'll process it and figure out, oh, it's the power button. I better do this and that, and so on and so forth. Okay? But the idea is there's a subroutine call. A subroutine call is going to use up the stack. So that means when your program is executing, this is your stack pointer. Okay? As far as you are concerned, in your thread, your stack pointer is here. If somebody press a button or enter or press on the key on the keyboard, it's going to call a subroutine. Calling a subroutine, which we'll see later on, will also use up stack resources. Which part of the stack is it going to use? Well, it's not going to chew up what you have already been using. That's yours. But anything below the stack pointer is up for anybody else to use. So your keyboard interrupt service routine, your power button handler will use up this part of the stack, which means the content below where the stack pointer points to can be changed based on what type of hardware event is happening. And your process is unaware of all of these things happening because when the subroutine to handle the hardware event is all done, it will restore everything back to here. So as far as your process is concerned, nothing happens. Okay? Okay, so we'll get to this part later on in more details. But the key question now is, then why is it not doing anything here? In other words, if I go back to this location, because remember at this point, this is after the pop instruction, the stack pointer is already back to this location. But if I subtract 4 from the stack pointer, that should still get me back to the location that ends with 9C. So let's check out those 4 locations and see if anything has happened. Nope, nothing has happened. But how could that be? Because I have been pressing the keyboard to enter the commands. Plenty of network events has happened in the background. The timer has been going off all the time. So there's a lot of stuff happening in the background. How come the stack is not clobbered? Based on what we have just talked about, it should be completely clobbered right now.
There's no location. The number of locations available is way too much. The probability of it changing.
That's not the reason. Once again, it is not a fair question because it is really an operating system concept in this case. The kernel, which is the deepest part of your entire operating system, has its own stack. Every single thread, every single process, every single program has its own stack. So when a hardware event happens, it does not use a user stack. It uses the system, the kernel stack. So that's why the stack that we are using as a user process is clean. It doesn't get anything here.
So,
Go ahead.
So it is predictable. You can rely on what was there. You can't know.
Well, I'm not sure about signals because signals is another type of asynchronous event. So let's check it out and see whether it makes a difference or not. We may not have a whole lot of time to do it, but I'll give it a try. A signal is basically a soft interrupt. It's another way to say, hey, program blah blah blah. I want you to pay some attention. But once again, it should use up some kind of stack space. The question is, whose stack space is it going to use? So what we'll do is we are going to find out who is running this program, ps-c test. How come it doesn't have a process ID? It should still be running.
Are you not an emulator?
Oh, okay, thank you. Wrong machine. There we go. Thank you. Okay, so it has a process ID of 1797. So when I say kill-usr1, which is just random, non-destructive, signal, 1797, it shouldn't do anything to the process because, it doesn't need to handle it. The question is, does it change the stack? No. Okay, it's still clean. So signal is, if I don't have a signal handler, it does not really actually do anything. So that's why, it's still clean. But in general, it's not a good idea to rely on the content below the stack pointer to retain the values. Yep.
So like hypothetically, like if this program was set up to accept input from the keyboard, then that might become an issue.
Well, yes and no, because you cannot, because to interface directly with the keyboard or the USB controller, you need to have access to I/O locations or input-output locations. But because Linux is a protected mode operating system, it does not let you have access to the I/O locations, and therefore you really cannot, poke and peek the keyboard handler or controller itself. Is that okay? Okay. So why am I still teaching you guys this? Because it seems like to us as end user processes, this really does not apply. But that's only if you're using a protected mode operating system. And under what situations is that assumption no longer valid? No, Windows is actually protected mode now. And everything since NT are protected mode. Okay? So what type of devices do not have quote-unquote an operating system? Well, most mobile devices do have an operating system. Like Android is Linux-based. Okay.
Like CCOM.
What's
In CCOM and stuff. It what starts the operating system.
Okay.
Inside of the.
What about this thing?
Inside of the motherboard.
Arduino. So if you look into Arduino, it is a fairly simple device, and let's check out the price right now. It's still pretty expensive. That is expensive. $25, for something like that is actually pretty expensive because the chip itself, which does most of everything, is only about $5 or $6 or something like that. Okay, but these chips are they don't have a lot of resources. Typically, they have 64, possibly 128 kilobytes to store programs. And you heard right, okay? I just said kilobytes. When was the last time you hear somebody mention that unit of measurement of storage? Kilobytes. No? You might have heard of your dad or grandpa talk about kilobytes or something like that. Yeah, but these devices are so small, they only have kilobytes of storage as far as program space is concerned. But when you talk about data space, where you store variables, the stack and the heap and stuff like that, it drops down to 2 to 4 kilobytes. Okay? Do you think we have space to fit Linux onto these devices? Not even close. Okay? And as a result, whatever program you develop on these things, this assumption cannot be held. Because your process, your thread, is the only thread of the entire device, unless you run a multi-threading kernel. Okay? But if you don't run a multi-threading kernel, which I have written one, then your process, your thread becomes the only thread. If you are the only thread, and an interrupt happens, whose stack is the interrupt handler going to use? Your stack. Which means whatever is below the stack pointer is going to be clobbered. So that's why I still want to mention this, because someday, who knows, you might end up programming one of these things. And why would anyone program one of these things? Where can we put these things, and why do you want to think about, hey, I might want to get into this type of programming?
Like robots, right?
Robots, yeah, we can put it into robots. Yep.
Like just basic different hardware controllers, or
Wherever you need something that is quote unquote intelligent. I'll give you one example because I just used one today. Screwdriver. Yes, screwdriver, like a normal screwdriver that you buy from Harbor Freight. Okay? Because how many times have you guys stripped a screw because you torque it too much? Okay, we have done it once in a while, right? So what if your screwdriver has the ability to measure the torque and give you a warning and say, hey, this is too much torque, most screws cannot handle this. Or the screwdriver, the material of the screwdriver itself cannot handle it, so you end up chipping the bit itself, which is bad. Okay? So the question is, am I putting a $20 part onto a $2 part to make it intelligent? The answer is no, because these things, the controllers can come in even smaller packages where they are less than 20-30 cents each. So you can put a 20 cents part into a screwdriver and sell it for, I don't know, 15 bucks. I think people are willing to pay that much money for an intelligent screwdriver. So the next question is, how does it tell you that you are putting too much torque into it? Assuming you can put a sensor, that's the easy part, but what about the output device? You put an LCD display on the screwdriver, how do you look at it? Your hand is over the over the LCD.
Make a sound.
Buzzer, LED? No. We got Bluetooth. We got Bluetooth.
Your screwdriver calls you and says, hey,
Your
you're pushing too hard.
screwdriver is going to talk to your cell phone, and you are going to write an app to talk to your screwdriver. So now you can customize your screwdriver and say, scream at me if I exceed 2 Newton meters of torque. Okay? You can program it. So when you're turning your screw and go like, and then suddenly your cell phone will buzz you and say, hey, you're putting too much torque onto your screwdriver, better stop now. Or if you put in too much, even after that point, it will automatically go to Amazon and order a new one for you because you will need it.
That's good too.
But it is not. This is not fable. This can happen today. If you can imagine putting a processor onto a screwdriver, where of course this stuff is important because that's the relevancy to what we are talking about in this class. We can think about what else we can put a processor into. How many applications can use a processor? Okay, the answer is millions. Okay, people just do not have time to write those apps just yet. Okay, so there's a huge opportunity out there to put embedded processors into just about anything. By the way, all the batteries that you use on laptop computers and cell phones, those are already smart. They have their own processors. Your battery pack has its own processor to measure how much charge is going in, how much charge is going out, and it can calculate how much lifespan it still has in order, in terms of capacity left, how much you can charge it. So it's already happening, okay? This stuff is already happening. It's just a matter of, are you going to get, hired doing this type of thing or not? So we are running out of time today for the lecture. I will be over at the lab for those of you who want to get a homework assignment done before spring break. Otherwise, you guys have a nice spring break, and I'll see you on the Tuesday after.
So I tried patching together the assembly code.